So this talk is about global scale tomography, and specifically we figured out, so we learned how to use a wave type that has practically not been used for tomography and which is abundant and abundantly samples the lowermost mantle. And now we can finally use it because the computational modeling has gotten there, and also the station coverage is much better than it used to be. And so it represents in a major step for my group, and these are the first two applications that I'm going to present. And the first is a new global mantle model, a P wave model that includes these core-diffracted waves, and that was led by Kasra Hosseini, first as a PhD student, and then it went into his postdoc, so it was a major undertaking. And the second is Maria Tsekmestrenko's PhD work that was on the Reunion hotspot and more widely the southern half of the African superplume, which is what interests us here. So the lowermost mantle is interesting because it's where the slabs finish and the plumes begin. And we've heard quite a few motivations already, so I won't go into detail, but roughly speaking, there are numerous ideas of how these elements interact in the lowermost mantle. And if you look at these four alternative cartoons, you can see there will be some significant seismic resolution needed to rule out any of these hypotheses or distinguish between them. So we do need resolution in that lowermost mantle. And the issue with body waves is that the coverage of the mantle is basically what you see here. That's true for P waves and also for S waves. And so you can see that the most homogeneous coverage is in the middle third of the mantle. At the surface, it can be very good if you're under continents that are instrumented. Problem is with the oceans. Those are the white areas. They are not instrumented. Let me just check this here. Yes. So these are the oceanic gaps. And then we're down here is also a blind area or blind spot where the resolution slowly tapers out. And that's because the P waves don't dive that far, and these P diffracted waves are not usable. That's the main reason that S models have been more used to interpret the lowermost mantle, for example, the LLV SPs, so they're shear velocity provinces, because P waves didn't used to see much. However, it's not that we have very high resolution with S models either, because S diffracted waves aren't used abundantly either. They are used, but but you do have normal modes which would put which sample absolutely everywhere, but at very long wavelengths. Okay, so the goal was to make these here usable, and so the red ones are wave paths of conventional teleseismic P waves, and then as soon as they start grazing the core, they get diffracted around it, and they are called P diffracted. And so this area is sampled extensively because they run a long path in here. Now these are just nominal paths. In reality, they look more complicated, and that's been the problem why ray theory that has been used very long for modeling isn't sufficient, and so therefore these waves have not been used. And what they look in data, you can see here, so this is a big earthquake. This is seconds after their first arrival. So here you can see the P wave coming in, and this is 40 degrees from the station, going to almost the other side of the Earth. And you can see these wiggles, so there's blue, and then a little red, and then a big red, so these are the echoes from the surface. And the character changes as you go to about 90 or 100 degrees. The wave becomes more washed out, more low frequency, and that's what's happening by the diffraction around the core. So we lose the high frequencies, and it's a different phenomenon then. And when we try to measure them, this is what we get for the conventional teleseismic waves. So of the attempts of measuring, so just any seismograms that you can record, you try to measure, and you have a success rate of something between 40 and 60%, depending on the frequencies that we attempt. So it's waveform fitting, and they are relatively high frequencies. But then as soon as you get to this range, you can see how suddenly the success drops, and that's where the frequencies get attenuated and taken out. However, even at the very far, almost antipodal distances, there's still about a 10% or so measurement success. So it just means you have to try often, and that's why the strongly increasing station coverage helps. And so we did that and processed the whole seismic database of the last 20 years waveforms, and got about 500,000 successful measurements. And so that is, that's orders of magnitudes more than has been used. And so what I'm doing here, what Kasra did here, is to project the nominal path where the core mantle boundary is being grazed. So that short segment is projected onto the globe, and you can see which areas are visited by these waves where they touch the core. So here a lot. And in general, the oceans are quite well covered, which is the opposite than the teleseismic P waves, which generally sample more under the continents. This was the big technical advance. They have to be modeled. So what does this wave sense when it comes back, when it has come back? And the sensitivity, so what it has seen of the mantle, looks something like this in reality. So it's not a thin, narrow ray, as I showed schematically. It looks like this banana that gets flattened when it touches the core mantle boundary, and that needs to be computed. And that's expensive, and it's done by full wave propagation. We also include the teleseismic waves that has been done, and that is with the method of Dahlen, which is much cheaper, and also PP waves, and ISC pics from the International Seismological Center included as ray theory. And so you can see the difference in adding the P waves makes to the sampling of the mantle. So here we have the model Detox P1, that's our first model, and it has only the conventional waves, the teleseismic waves that P tomography so far have had. And this one is exactly the same, everything the same, except that P diff waves are added. And so you can see 600 kilometers, there's basically no difference. 1200, there's really not much difference either. But then here we get into the lower third of the mantle, and you can see how the oceanic gaps are starting to close. And then at the core mantle boundary, it's a huge difference. The P waves basically lose all sensitivity, and the P diff waves sample intensely. And the result of this is this model, Detox P2, which is shown here at the core mantle boundary. And it looks quite similar to S-wave models, which is a good thing, because the S-waves have seen these regions more intensely, in good part thanks to the normal modes. So we have the large low shear velocity provinces with significant substructure, and here the slab graveyards, the biggest one under Asia, and here. And I'll show more of these, so you'll see these again. And comparing this to previous P wave models, so first I'm comparing, so this, Detox P2, to our own Detox P1, which is where we haven't included the P diff, which is almost blank. And then you can see the other models. So this is the Princeton model from 2005, and this is the MIT model from 2008, both much used, but I could have shown others as well. They have more structure. What's that difference? Well, because we now have so much P diff data, we can afford to robustly damp the teleseismic waves. That means we can make sure this model is really stable, and the teleseismic waves only have to talk about the upper 2/3 of the mantle. Here, very likely, this was less conservatively regularized, and that doesn't mean it's wrong, but it means two things. A, that it's very likely that some instabilities will have been introduced, so you don't know what are unstable artifacts here, or it's difficult to say. And the other is that certainly the waves weren't modeled quite correctly that sample these lower regions. So in practice, they were already P diff waves, or had P diff character, but weren't modeled as such. So you also get a smearing due to that. However, you can see, I mean, a lot of the features that are in this one are also present in these. And so in retrospect, there's certainly a lot of this being validated. However, if we want to look at the differences, so here I've taken the MIT model, which has been much used to interpret subducted material in terms of paleo trenches. And here I'm contouring in 3D all the seismically fast material. So that's slab at these depths in the middle third of the mantle. And now color is depth. So it changes every 200 kilometers. And what you can see are the Mesozoic orogenies, basically, so the Tethys orogens and the American Cordilleras. And now I'm going to look at the lower third of the mantle in this MIT model. And you can see that by comparison, it almost goes blank. And also the anomalies aren't as elongated anymore. They get more blobby. And in general, they're just, in the southern hemisphere, there's nothing, right? So you strongly suspect there's stuff missing. And now, by comparison, this new model, so you can see suddenly, I mean, these are exactly the same depths. So suddenly the brown, that's the deepest, that's the core mantle boundary. There's a lot more structure. And at the shallower depths, the slabs become much more elongate, so trench-like, as you would expect them to be a priori. And if we look at Southeast Asia, again, a comparison of these two models at the core mantle boundary, there's this big slab graveyard under East Asia that talks about the Paleozoic assembly of Asia. And it's the best illuminated aspect of existing models, so I'm comparing it. And if you're now asked to put paleo trenches, it's difficult what you would do here. Whereas here, that seems much clearer now, where the subduction zones would have been. And so getting over that, that increased confidence allows us to finally interpret these oldest slabs. And then we've just spent an ERC basically doing that. So for that, this progress is really important. In general, P wave models have been the preferred tool for interpreting slabs. So that is a main application. However, this is a session about upwellings, so I'm coming to the upwellings. And the large low shear velocity provinces. We've briefly looked at them, and now this is a different map projection. So now we're centered on Africa and South America. And please just disregard all of these cuts. They have nothing to say. The triangles are hotspots. Okay, so now in this picture you see is actually not so much a picture of two LLVPs anymore, right? Rather we have, so this is the African LLVP with a lot of substructure. Now the Pacific one is subdivided because we go around the map edge here. But very clearly the Pacific one is divided into these two regions that also show up on S models, but it shows up very clearly here. So this is the feature that Stephen Grant talked about yesterday under the East Pacific rise, and where Stéphanie Durand told us that it really only shows up when the normal modes, the odd degrees are added. But the biggest change is that there's a lot of red structure here that makes a bridge between this African and the Pacific anomalies. So it almost becomes a continuous belt that's only interrupted by this Asian slab in the Indian Ocean. And that difference is really not present like that in S-wave models. I've seen a lot of, I've looked at all the pictures that you've shown, and sometimes one spots a little bit. In most S-wave models, it's just not present. And we can see that here in the comparison. This is Sigloch of Stéphanie Durand. So here we can see what normal modes alone can do. And now, so with the odd degrees, we do get this East Pacific anomaly. And the division here is more or less clear. I mean, we can see hints of it, but clearly under South America, there's nothing in the S-wave models. So that looks like a real difference. And if we now go back to the P-wave models, I mean, okay, we're maybe less confident in these, but yeah, so here we don't see something, but here there is some hints, and there is also some hints. So this may really be a difference between P and S waves, and it would be interesting to see what that means about the mantle. okay, the relationship between these LLVPs and plumes. One hypothesis is this: we have thin plumes, but they just smear together in a tomographic image, and so we tested that. We put in synthetic plumes in all the hotspot locations and did a resolution test, so inverted, and this is what comes out. Thinner plumes, this is what comes out, so you can judge whether these results look like the real mantle. It doesn't really look like it. There's more hot material down there, so they shouldn't smear together that much. So I think that one we can rule out. So this is a hemispheric scale study then, and we did it because so it involves all this hotspotty area, and we did it because we managed to instrument one oceanic hotspot. Usually you don't have resolution in the upper mantle because the ocean is not instrumented. In this case, we got a dedicated experiment to instrument 2,000 times 2,000 kilometers around this hotspot, La Réunion. And it means you have to work with ocean bottom seismometers, which is a lot of effort. And also the data are more challenging. So that's what the experiment looked like. What you get for it is that before, so this is a vote map of tomographic models. It basically asks 26 models, do you think this voxel here is slow? And they all say yes, because it's dark red. And here it asks, do you think this voxel is slow? And they all say no, and that's why it's white. And so if it's light red, half of them say yes, and half of them say no. And what you can see here, there's huge agreement about the the LLVP with its sharp edge. I mean, that's an amazing feature. Everybody agrees. But then as you get here, it's about a half and half. So the models just can't decide, and there's no structure, and that's because there's no instrumentation around this hotspot. And then now our tomography result then also gets this African super swell, and then a lot of structure here. And that's what I'm going to show you now. It's complex structure. So this is Maria's tomography model in this region. In 3D, it's very important to look at it in 3D, but it's also difficult to see what's going on. The color scale is as with the slab, so the lowest material, and this is only hot material now, or slow, is red, and then it becomes yellow and green. Maybe don't look at these arrows because you won't be able to follow so quickly. And what we're doing now is, so just look at on this side, and we're going to step from the lowest levels to higher and higher levels, and just see how the structure develops. So here at the CMB, it's a very compact structure, the LLSVP, and it has a certain concentration here, and then it has some appendages, in particular one that goes here, one that goes towards afar, and maybe a little one here. Now we step up. So I step down again and up. It's still more or less as it was, so we're at 2,300. We step up, and it becomes a bit more fragmented, and we have we're sort of centering on a core here that's under South Africa. And now we step up. We still have this cusp, and there's not much other structure around anymore, so it's very compact. And now something changes. So you can see we're stepping into about halfway through the mantle, and what's happening is that this disintegrates into three anomalies that diverge a bit like a Mercedes star. And as we keep going, we can follow all three of these outwards. So one goes up the East African rift, one goes in the southern Indian Ocean, and one seems to go to Bouvet. And at these steps, so now we're at 1,000 kilometers, which has been talked about quite a bit, and the structure becomes significantly more complicated. But it still diverges outwards from this center, so there's no structure here anymore in the center, and this is the shallowest I'm going to show. It's again, so we're still going towards afar, and it's getting more complex. Oh no, there's one more. Okay, so here we go, East African Rift, Reunion area, also something going towards Kerguelen. Okay. Okay, so one thing we can then say is this is a special depth, about 17 to 2,000 kilometers, is where the LLVP seems to be cusping, and at the next step it diverges. So there are 3 branches going out here. And the other thing is that this is the lowermost mantle, and if we look at everything on top of it, you can see that there is the shallow structure, the shallow slough is only above where the deep is. So you have green only above the red and not in other areas. Specifically, you have green above this corridor here, the South Indian corridor on the CMB. You have it above the Zafar corridor. Then you have another corridor here where there's no green, so okay. And there's a bit of an exception. So we have green here, even though we don't ever have a red under here, but the resolution tests show that if there would be a CMB, a red corridor here, we wouldn't resolve it. We don't have the data. Okay, so is 5 minutes? Okay, thanks. Okay, so let's look at these 3 branches of that Mercedes star that all have this element of, so here's the one under reunion. So it's cutting like this, east-west, South Africa. So here we can see this cusping LLVP. This is the corridor on the CMB that runs into the Southern Ocean, Southern Indian Ocean. And from here, this cusp, we have this branch go up into the mid-mantle. That goes diagonally up, and in the upper mantle, it becomes more complicated, but there does seem to be a conduit towards reunion. And there's definitely no connection that goes directly down from reunion to the core mantle boundary. So a connection is only via this structure. And the upper mantle in general is quite complicated. The other 2 branches is a north-south section. Again, we have the LLVP that cusps here. And then we have one branch going diagonal towards Kenya and Afar. That's this. And we have another branch that goes diagonally towards Bouvet. Just quite poor resolution here, but the overall structure seems to be like that. Okay, and so in general, we seem to have 3 specimens of this element. So we have a corridor on the LLVP. They come together in this central area under southern Africa, and then there's a mid-mantle branch that reaches to about 1,700 kilometers, and then we have something smaller scale going up from there. And this passes resolution checks. And so what's going on here, I mean, we think, I mean, that's our proposed explanation, is that we have 3 of these elements. The crucial thing is that this diagonally trending structure in the middle mantle is vertically above the CMB corridor. And where there's no CMB corridor, there's also no shallower structure in the mid-mantle. So why would that be? Well, the easiest explanation seems to be that the thing in the mid-mantle came from that corridor, so detached from it. So it would be a sequence like this. We start at a peripheral end by Kerguelen, and we develop an instability that starts to rise. So that's what we're seeing here. And as soon as that is gone, this one becomes unstable because now the temperature gradient to all sides is large here. So now this one starts to detach. This has become the periphery. And they slowly keep rising, and then we get the third one that also does that. And then that could explain why we see this structure that is vertically above the CMB. It also is consistent with geodynamic models seeing these things rise vertically rather than, so theoretically material could flow like this through the branches, but that would be difficult to reproduce in simulations. The tomography does resolve these individual plops, and so we think what happens once it arrives at around 1,000 or so kilometers is that we get the thin conduit plume phenomenon and some other complicated stuff in the upper mantle. I mean, we now have resolution under reunion, and it's certainly not as simple as just one single conduit. There's more spreading out. And so that then would mean that if, you know, either it stagnates here or it keeps slowly rising, but in any case, probably the less viscous material starts shooting up into the less viscous upper mantle, and some of it gets to the surface and some of it spreads out. It means that a plume is anchored in the mid-mantle rather in the lowermost mantle, but it would bring the chemical signature from the lowermost mantle because ultimately it got there. Essentially, it's like a Morgan plume, but it lost its tail. And so that should give some constraints on the rheology. Okay, that's my last slide. It's the question, what does this, you know, what are the geologic manifestations or consequences of this? So one thing is, I mean, this is a very pronounced, this is the most beautiful corridor. This is the most recent one. In either case, you know, so here we had an inward sweep of Kerguelen, 120 million years, and LIP Crozet, Marion is around here, 90 million years, and Reunion 65. So that was a temporal sequence along this corridor as proposed in this model. Afar was 30 million years ago, and there's clearly you know, a continued rifting that progresses southward. Now that could be just in a shallow mantle, but you know, maybe it's the deep mantle. I mean, maybe it's already feeling the second blob that's coming up under Kenya, and that is imaged. So this would have been a sequence that opens the Indian Ocean just by definition. That was the events that severed India from Gondwana. So that's what creates the mid-ocean ridge. And here maybe we're creating a mid-ocean ridge. So that could be a very direct connection between the lowermost mantle and the face of the Earth. And then it's interesting to speculate what is happening here, where there's a convergence of three lip-producing corridors. Certainly all of Africa has a component of dynamic topography already. And yeah, maybe there will be a super plume eruption. Thanks.